Hi, this is Gabe Rogers, and this is Physics 2, Lab 4, Circuits. The purpose of this is to understand the differences of parallel and series circuits, and measure potential difference in amperage voltmeters and ammeters. Also, we'll be going over RC circuits and how they work. And then concepts use Ohm's law, capacitance, the node rule, and the loop rule. Part 1, we have series of parallel circuits. To the right is a description of an example or image of two of the parts of the lab. And on the circuit we have basically two 1.5 volt batteries making a total of 3 volts, 47 ohm resistor and 100 ohm resistor, and a total of 147 ohms resistance throughout the entire circuit. And we have two ammeters for the left one, and then for the right one we have one ammeter and one voltmeter. Through the calculations, we find that the current is 0.02 amps. The difference in voltage of the battery is 3 volts, and the voltage of the 47 ohm resistor is negative 0.959 volts, and the 100 ohm resistor is negative 2.041 volts, which is a total of negative 3 volts for all the resistors combined, making the net voltage 0. Part 1, here's a graph basically showing how the voltage changes. And why does the addition of the voltmeter change the ammeter reading? The voltmeter has an almost infinite resistance, therefore little current flows through the voltmeter, so the ammeter does not change. When the ammeter connects in parallel with the 100 resistor, both the ammeters read 0.6 amps because they bypass the 100 ohms for the path of least resistance. So they just bypass the 100 resistance thing completely, leaving you the 0.47, which is 3 times less resistance than before, making it 0.06 from 0.02. The resistance of the resistors is followed 47 ohms, and then the R100 is 100 ohms. The wire is 0 ohms, and the ammeter is 0 ohms because they are ideal. In real world, the wire and the ammeter would have some resistance. Part 2, this is the RC circuit, which means it has a capacitor. The formulas are on the top right that we used. And then what happened to the 10 ohm light when we plug it in to the capacitor and there's no battery? Basically, it becomes very bright and slowly dims until it turns off. Because the capacitor, once it discharges. And then what happens when the battery is disconnected and the capacitor connects to the light? The same thing. As the capacitor charges, it pushes back against the current, slowing it down and eventually becoming nothing, which makes the light become bright and slowly dims until it turns off. Now what happens to the current when the capacitor is charging from the battery? Starts off large and increases to 0 as the capacitor charges. And the time for the capacitor to charge and discharge is 9.4 seconds, and the time capacitor to charge it from the 20 ohms bulb is 18.1 seconds. Here's the graph of the voltage change over time across the surging capacitors, and basically it follows this kind of curve, change in voltage over time. And discussion questions: what if you're doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? What differences about a real ammeter and how it would affect the circuits you hooked up to? Ammeters have some level of resistance and lower the current values, unlike the ideal model. And then what if you're doing this lab in real life and use a real capacitor with no resistor in a circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would prediction happen in real life? Explain. And then ideal model would charge instantly with an infinitely large current. And then the answer is no. Prediction would not happen in real life because there's resistance in the wire. And that is it for me. Thank you.